the three-body problem, the book, is going to be a Netflix show. And so it's a duty. I've been officially sworn in as the duty to do this as a physics problem. So, I mean, there's some spoilers here, but essentially, we can think of the three-body problem. It's obviously the three-body problem. It's actually more than that. But imagine that I have three stars interacting with each other, and then I'm gonna model this. I'm gonna show you how to model this, and then we're gonna model a stable orbit of three objects, and then we're gonna add a planet. So it'll be a four-body problem, which is not the sequel. But here we go. So imagine I have these stars, 1, 2, 3, and they all have vector locations, R1, R2, R3. And they have some momentums too. Well, they all have a gravitational force interacting between them. So let's just look at this one. I'm going to draw this vector, R1, 2. R1, 2 is the vector from 1 to 2. So that's actually R2 minus R1. Now I can calculate the gravitational force on 2. I'll call that F12. F12 is going to be negative G M1 M2 over R12 squared R12 hat. So I can get a vector value for that force, right? Because if R12 is this way, the force on 2 due to 1 is going to be pulling that way. That's why there's that negative sign. R12 is needed to make this a unit vector. So this is our gravitational force just between those two. Now, there's also going to be a gravitational force between, right here, 2 and 3. So let's actually do this differently. I'm going to say R2, 3 is going to be the vector from 2 to 3. Okay, that's going to be R3. And my convention here is kind of useful because you're going to make mistakes if you don't do that. Minus R2. And then F2, 3, I'm going to use the same convention. This is the force on 3 due to 2. So negative G, mass 2, mass 3, R2, 3 squared, R2, 3 hat. Now, I need to find the net force on object 2. And I'll also call it F2. It's going to be equal to F12 minus F23. This is the convention I'm going to use, right? Because I need to add up all these forces, but I don't want to have to recalculate this. Since I have 2, 3, the force on 2 due to 3 is the opposite of that. So that's why this is negative. But this is a 1, 2, so it's fine. And then I'll just do the same thing for F1. It's going to be equal to negative F1, 2. And then I'll do minus F 1, 3, and I can do that for all of them. Now, once I have the forces on them, now I can use numerical calculations to find the motion. So what I'm going to do is say F2, that's the net force, is the change in momentum of 2 with respect to time. So if I break this into short time intervals, short time being, relative, then I can write this as, now I have an index problem here, but I'm going to do it anyway. This is going to be P22 minus P21 over delta t. So this is the momentum at the end of the time interval. That's at the beginning, and I get P22 equals P21 plus F2 delta t. So I can update the momentum. Then I can do the same thing using the definition of average velocity. I don't want to spend a lot of time on this because I've done it like a billion times. And I get R2 equals 2 is R21 plus P22 over M2 delta t. So this is just updating the position using the velocity. So what I'm going to do is to take the positions of all these stars. I'm going to have their initial momentums. I'm going to calculate all the forces, use those forces to update the position, and then redo it. Let me get this working, and then we'll make a stable system. How's that sound? Okay, so just like in the book, and maybe the show, the three-body problem. So let's switch over here to the computer. Of course, I'm going to do this in Web v Python. Web v Python is just my favorite thing ever. I'm looking at my value of my mass right there. Okay. So I did that print one just so I could save. I find, and I don't know if you know about this, but for me, if I try to save a program before I run it in trinket.io, not in glowscript.org, in trinket.io. If I save it before running it, it like saves 3 versions of it. It's really kind of annoying. But if you run it once and then save it, I don't know. Let's just put our stuff in here. I need some constants. G equals 6.67 times 10 to the negative 11th. That's easy. The mass of, I'm going to just call the mass capital M. I'm going to have 3 stars that are going to be equal mass just because that's just going to make things easier. And it's about the mass of the sun. I don't know. It's a book. So 2 times 10 to the 30th is fine. I also need I'm going to need this. I'm going to need the astronomical unit because I want to make it, reasonable. So 1 AU is a thing that I can put in my head just to kind of scale everything. And that's 1.496 times 10 to the 11th. Now I'm going to need the radius of the stars, RS. I'm just going to put these at, make that a little bit bigger. Let's put the radius of each star at AU over 100, which is terrible value. But if I don't do that, I'm not going to be able to see them. So I want to be able to see them. And finally, yeah, that's it. So let's just make 3 stars, and then we'll run it. And I want to put them at just some random location. I'm just going to randomly pick things and give them some random velocities and let them move around and see what happens. So S1 is star 1. It's a sphere. You could do this as a list, but I want to do it as simple as possible. So let's put this at the origin, this one at the origin. Vector 0, 0, 0. The radius is equal to RS, and of course the color should be yellow. And then make trail equals true, just because that will look cool. Okay. S2 is another one, sphere. Position equals vector. I'm going to pick something in terms of AU. Let's say AU over 10, AU over 6, 0. And then the radius is the same. The color is the same. And the make trail is the same. Yes, I'm going to give you the code at the end. Don't worry about that. And then I'm going to copy this one, and paste it, because that way I can just change things. Because I'm not going to change all that stuff. I'm going to make this S3. And then the position, let's put this negative AU over 20. And then just AU over 12. I don't really know what I'm doing. Okay. Let's run that and see what it looks like. There's my 3 stars. Random. Okay, I do need to give them some initial. I could just let them move, but I want to give them a little bit of velocity. So let's give them momentums. S1.p equals m times vector 0, 0, 0. Let's make a scaling value v0 just for now of 1 times 10 to the 4th. Let's just pick something. S2.p equals m times v0 times vector. Let's say it's moving in the -1, -1, 0. I just made that up. And then S3.p equals m times v0 times vector. Let's make this one go even slower. 0.1, 0.20. I don't know what I'm doing, just picking some values. Okay, now I need my time. Time is 0. My time step, now that one's difficult to imagine, right? Because how small of a time step do you need? You're not going to use a second. That's way too big. That's really way too small, I'm sorry. So let's do an hour. Maybe that's too small. Maybe that's too big. I don't know. So an hour is going to be 3,600 seconds. I need it in units of seconds, though, because all my values are in seconds. While, let's run this for 2 days. So while t is less than 2 times 24 times 3,600. I know this is terrible, but that's just fine. And the rate of 100. So you can't even see that. Look at that. Can't even see that. Yeah. So rate tells the web vPython how many loops to do per second. So don't do more than 100 per second. That may be a too slow or fast for the animation. Let's just play with it and find out. Now the next thing I'm going to do is calculate R12, what did I do? R13, and then R23. So those are the 3 vectors I'm going to create. I'm going to calculate. So R12, my convention says, is the vector from 1 to 2. So that's going to be S2.pos minus S1.pos. This is going to be S3.pos minus S1.pos. And then finally, S2.pos, final minus initial, S3.pos minus S2.pos. And it's kind of useful to get this convention so that you don't have to like, oh wait, which way is it going and all that stuff. Now I can use those to calculate my 3 forces that I'll use. So F12 is going to be equal to negative G times M. I'm just using, I didn't assign that as a property, times norm R12, divided by mag R12, R. And then I can copy that. And I can paste it. Now I can just change this to 13. 13, you have to say it out loud. If you don't say it out loud, it doesn't count. 13, and then I can paste it. I can change this to 23. Wait, what did I do? I did 23. 23. 23. No, 23. Okay, so now I have my forces. Next, I'm going to calculate the net force on all my objects. S1.F. I'm going to call S1.F the net force on object 1. And so it's not, it's kind of bad because F, the force is a property of multiple objects, but I find this works really well. So I'm looking over here, I have the force that 1 exerts on 2, so I want that backwards. So I can say minus F12. And then I have here, again, it doesn't end in a 1, so it's going to be minus F13. Now S2.F is going to be F12, right, because that ends in a 2, and down here, that one does not, so it's going to be minus F23. And finally, S3.F is going to be equal to F13 plus F23. Now I'm going to update the momentums. S1.P plus S1.F times ET. S2.P equals S2.P plus S2.F times ET. S3.P. Do you guys like me typing this stuff? Someone said, oh, live coding's the best. But it seems like, it's kind of boring. I mean, if you like it, you like it. And that's cool. And I really respect that. And I appreciate that you like that. I like it. So now I'm going to update the positions. S1.pos, S1.pos plus S1.p times dt divided by m. S2.pos equals S2.pos plus S2.p times dt divided by m. S3. I was thinking, I took this typing quiz the other day, and I remember in high school I wanted to take basic programming, and you had to take typing on a typewriter. And I was like, this is stupid. It's not stupid, because now I can type. Okay, now I need to update time. Now, if this works, because I've been not really paying attention, I'm gonna really impressed with myself. But let's save it and run it, and just see what happens. Okay, it blew up. Maybe that's too fast. Let's see if let's put all the velocities at 0 so that we can see what's going on. Maybe I give it too much of a velocity. Let's put this at 0. They should just attract towards each other. Okay, too fast, I guess. Too large of a time step. Let's just do that. Let's just do 100. Still too fast. Let's do 10. I was gonna change the rate, but wow, what the heck? Let's change this to 10. What am I doing wrong? They're just blowing up. Let's do this at 1. They just blew up. Do I have my forces wrong? Are they too close together? Maybe they're too close. Let's put this at 2, 2, 1. Okay, what are they doing? Okay, there's something wrong for sure. Okay, R12 is the vector from 1 to 2. Right. SR, do I have like a negative mass? Something's weird. Vectors. V0. That should be 100. Okay, R12, R13, R23, F12 is the force on 2 due to 1. That's right. Right? So if it goes R12 goes from 1 to 2, and I'm calculating the force, it should be negative, right? F13, 13, 23, 23. Okay. The force on 1 is negative F12. That's right. What am I doing wrong? Okay, let's see. Of course, you know I pre-programmed this too. So let me just see if what my old one says. I did it for my blog post, but my trinkets. You know, I could just stop the video and start over, but I don't want to do that. I've already had so much fun. I could edit it too, but I don't want to do that. Okay, that one's working. Let's see. So, mass, G, S1. I have those at AU over 10. I have DT of 200. 1, 2, 1, 3, 2, 3, 1, 2, 2, 3, 1, 3. That's the same thing. Oh, you know what? I bet it's down here in the momentums. Okay, so that's fine. That's fine. Oh, I see what I did wrong. Okay, this should be squared. I bet someone was like 5 minutes ago, you didn't square the forces, dummy. And then they probably left. And like, this is stupid. Okay, so they're not blowing up anymore. That's good. Now let's just increase the rate. What am I? Oh, rate at 1. Okay. I think we're going to be okay now. Are they moving? Let's put them closer together. Let's just increase the rate. Okay, closer together it is. Okay. I did this AU over 10. And then let's make that 12 and make this 20. Now they're closer together. There. Okay. Yes. 3-body problem. Now, if you want, you can check. It looks reasonable, so I'm fine with that. It looks reasonable, but you could check the momentum, see if momentum is conserved in the X direction, the Y direction. You can see if energy is conserved, but I'm not gonna do that because I want to make stable orbits. I don't want to make a 20 million minute video, even though that would be fun. So let's look at how we can make these in a stable orbit. There's multiple stable orbits for 3-body problems. One of the premises of the book, spoiler alert, is that it's difficult to predict the motion of a 3-body problem. Okay. So let's go back over to paper, and I'm going to show you my 3-body problem that I want to calculate. Here we are. Okay. In the book, the Tri-Solar Syzygy, that's the event, the Tri-Solar Syzygy. I don't even know what that means. That's fine. They say the 3 stars line up in the sky. So what we have is a star. This is one possible way. A star and a star. And then the planet would be over here. And we'll put that in later. So this is going to be moving this way. This is going to be moving that way. And that one's stationary so that they move around in a circle like this. Now that is indeed possible to get it to work. Because in order for this to move in a circle, it's going to have a net force that way. And we can say the magnitude of that F net is equal to mv squared over r. So this is, we'll call this RO for the orbital distance. Okay, so I'm going to call this one 1, that one 2, and that one 3. 1 gets to stay in the middle because it's the most magical, I guess. So let's write an expression for F net. So this force, these two are going to interact, and these two are going to interact. And they're both pulling to the left. So F, and I'm going to leave off the vectors and stuff because we're all in one dimension here. F net, and that's my positive direction. It's going to be this force, which is G m squared over r0 squared, right? Because that's the distance r0. This force is going to be plus G m squared over 2r0 squared. Right, I have 2 of those. And that's going to be equal to the mass, m, times the velocity, v, which I'll call it v0, but this is called v for right now, squared over the circular radius of this, which is r0. Now, suppose I pick the value of r0. I want to find out how fast this is going. So I want to solve this for v. This mass cancels. That's fine. I can multiply both sides by r0, and I get v squared equals g m over r0 plus g m over 4r0. Right, because I have to square that too. So now if I add these two together, this is 4 over 4. So I get 5/4 g m over r0. And then I take the square root of that. So v is going to be the square root of 5 gm over r0. So let's pick this as au over 10. Okay, that's going to be my distance. I'm going to line these up. I'm going to put this one at the origin, that at r0 plus r0 in the x direction, minus r0 in the x direction, and then I'm going to give this a velocity in the y direction, that a velocity in the z direction. Let's do it. Okay, going back to the code. Here we are. So I got S1's already in the right place. Let's call this RO equals AU over 10. So I'll just put this at RO 0, 0. And this will be at negative RO 0, 0. Let's just run that to see what it looks like. What happened? Can't find RO because I can't type. Good thing. See, that's why it's nice to run these things. They should just crash into each other. Yeah. And then they explode because of problem with the time step, and that's fine. Now I need to calculate V0. I'm just going to put this in here. Square root of 5 times G times M divided by, 5/4. In my paper, I left out the 4. Divided by 4 times RO. That's my V0. So S1 is going to be stationary. This first one is going to be vector 0, 0, 1, 0. So it's going to be moving up. And the other one's going to be 0, negative 1, 0. That should be it. It should run now, right? Because I lined them up. One's going up, one's going down. It should be a stable orbit. But who the heck knows? Okay. Let's let it run for a longer amount of time. Let's make this 20 just for fun. So there's our tri-solar 3-body problem, and it does indeed look stable. They wouldn't actually leave trails, but I'm pretty happy. Okay, now we need to, one of the things in the book was to put a planet such that it has the same angular velocity, right? So that those all stay lined up. I mean, it doesn't have to be that way, but I'm going to do it anyway. So I want to find out where that planet would have to be in order to be in a circular orbit with the same angular velocity. It'd be like a Lagrange point. It would be a Lagrange point for this 3-body problem. Okay, so let's go back over to the paper and calculate that. This is a little difficult, but that's fine. We can do difficult stuff. Okay. So here's my 3 stars. And I know I'll call this V0. And I know this is RO. I guess I call it V0. And then I want to put a planet over here. This is Tri-Solaris. That's the name of the planet in the book. And it's going to be a distance RP away. And the thing is, I want the angular velocity of this and the angular velocity of that to be the same. So omega for this one is going to be V0 over R0, and that's going to be equal to V planet over R planet, right? So I can find V planet, and then I can let it go. Now, there are 3 gravitational forces pulling this way, right? So let's calculate the net force on that one, on the planet. It's going to be equal to this force, which is going to be G, mass of the star, mass of the planet, over RP squared. Right, that's just the distance. Now this one is going to be equal to plus G mass of the planet over RP minus RO quantity squared, right? Because this one's a little bit closer. So I have to take off that. And now this one's a little bit further. I have to add that on there. So plus G mass of the planet over RP plus RO quantity squared. And that would be equal to M V squared over R, or omega squared R. So I'm going to say V0 squared over R0 squared. That's the omega times RP. M omega squared. V squared over R. Right. Yep, that's right. Okay. So I can cancel this mass. But other than that, I don't really have much I can do. So this is not, since I have this weird thing down here, it may be solvable. Okay, I'm not really sure, but I don't wanna solve it. So instead, I'm gonna cheat. What I'm gonna do is to pick a value of RP, and I'm gonna solve for this right-hand side, and then I'm gonna solve for the left-hand side, and then I'm going to plot both of these versus R, and when they cross, that's when RP is equal. They're equal. They have the same value. And that would be the solution of RP. Okay, so yes, I'm going to do this in Python. Let's do this in Python. Computer. Okay, I'm going to open up a new program. New. Me. No, I didn't do it. It did. I have it zoomed out so much. Just so you can see, zoomed in, and web v Python, and I want code. Okay, G1 equals graph, X title is going to be equal to RP, and then Y title is going to be, technically it's the acceleration, so I'm just going to call this A, right? Because if I divide the force by the mass, I get the acceleration, so it's units of acceleration. That's kind of useful later. And then width equals 400, height equals 200, and then I need two graphs. FR is the right-hand side, G curve, color equals color dot blue, and then FL is the left-hand side, G curve, color equals color dot red. Now I need G. I need all my stuff from my other program. Is this the same? Is this the one I was working on? No. It is this one. I just want these values up here. I don't want to rewrite them. Why rewrite them when you can copy them? Not G equals G. Okay. M. That's good. RP equals. Okay, so I need to start with the value of RP, and it needs to be somewhere. It's got to be greater than RO, right? So let's just start with this at 1.5 times RO, and then I need how big of a step am I going to make? Let's say DRP is, I'm thinking here, what about DRP is AU over 100? I don't know. And now, while RP is less than, how far out am I going to go? Let's go to AU. We're going to have to change this, right? We're going to have to change this. So I'm going to move out to 1 astronomical unit. I don't care about the rate, so I don't really care how fast this goes. I just want to calculate the left-hand side and the right-hand side. Left-hand side is equal to G times M times 1 over RP squared plus 1 over RP minus RO squared plus 1 over RP plus RO squared. Then my right-hand side is V0. Do I have that V0? Okay, let me copy that. Tri-Solar V0 right here. That's the velocity of the thingies. GM. Okay, so I can do that. v0 squared times rp divided by ro squared. And then I'm going to plot both of those. So fr dot plot rp right-hand side, fl dot plot rp left-hand side. Now I'm going to increase my value of rp. rp equals rp plus drp. Run. If this works, I'm going to be pretty impressed. I get to be impressed with myself a lot. Okay, there. We found the answer. Done. It's right there. But let's say, look, I'm going up too far. Let's go to, let's say, let's plot that in AU just to make it simpler to see. RP divided by AU, since I have the value in RP in AU, AU divided by AU. Okay, so that is 0.2 AU. So let's just do this up to 0.2 times AU, just to zoom in a little bit. There you go. So over here, they cross at 0.176 AU. So 0.176 AU. Although that looks a little janky. Look at the step size is too big. Okay, let's change that step size to something smaller. DRP divided by 10. Oh, now that's bad. Did I get an error? What happened? DRP divided by 10. Oh, I want it smaller. I forgot how to divide. And now I get 0.176. So let's do that. So let's go back to our other program. And we're going to add, I'm going to put RP equals 0.176 times AU. Okay. Now let's add that planet in there. So the planet is going to be equal to a sphere too. So let's call it P1. Planet 1, sphere. Position equals vector RP00. 0. The radius, it should be smaller. So let's say RS divided by 3. And let's leave it as white. And then make trail equals true. Now, I'm not doing a real four-body problem because I'm going to assume the mass of the planet is so small that it doesn't influence the mass of the stars, and so we don't have to worry about that. I have P1. Now I need P1.P. Let's get the mass. Let's call it M, 1,000. It doesn't really matter. I'm going to divide by that anyway. P1.P equals M times. Now, it had a velocity of omega, which is V0 over R. So if I take V0 times RP divided by RO, so that should be the velocity. Okay, good. Now down here, I'm going to need to calculate 3 more vectors. All of the vectors to the planet so that I can calculate the gravitational force. R1P is P1.POS minus S1.POS. R2P equals P2.POS, no P1, minus PS2.POS. And then R3P equals P1.POS minus S3.POS. Now I'm going to calculate the force in one fell swoop. I'm going to call it FP. Let's just call it P1.F is going to be equal to negative G times M. They all have that. Times M. Times 1 over norm R1P divided by mag R1P squared plus, the minus sign's out there, plus norm R2P divided by mag R2P squared plus norm R3P divided by mag R3P squared. So that's the force. Now, when I go down here to update the momentums, I'm going to add in the planet. P1.P equals P1.P plus p1.f times et, and I need to update the position. Again, I'll be very surprised if this works. P1.pos equals P1.pos plus P1.p times dt divided by m. Let's run it. I should save it, shouldn't I? Cannot add a scalar and a vector. Okay, that was dumb. Where did I do that? Okay, so I added this. Oh, no, that's fine. Oh, aha. That's a scalar, right? I need to multiply this times. Let's put that in parentheses. That scares me. Times vector 0, 1, 0. Okay, I think that's it. Okay, so you'll notice that it's not perfect. It's not perfect, and I suspect it's because of the way that I but it's pretty good, and I'm pretty happy with that. The way I calculated the position, right? I just didn't get an accurate enough position. If you get that more accurate, it's going to stay in there longer. Now, there's another way to make it orbit a system like this. If I move it farther away, then what's going to happen is I can treat these all as just one mass at the center as a very rough approximation, and you can get a pretty good orbit there too. So, okay, let's talk really quickly about this. This right here, notice that I plotted this as acceleration. So acceleration of 1.3. 1.3 is the acceleration of the planet as it goes around 1.3 meters per second squared. So would the people get pulled off of the whole thing? No. Not really, right? Because if it's like an Earth-sized planet, the acceleration towards the center would be 9.8. The acceleration, the gravitational force pulling towards the stars would be 1.3. But even then, the whole planet's accelerating. So it's not the same as just having a stationary planet and the stars pull them off. In fact, this is exactly like what happens with the tides, right? So it's the idea that the Earth is a rigid object, and we're calculating the acceleration of the center of that object. So if you're on the surfaces of it, you're gonna have an acceleration equal to the center, but a different gravitational force. So this is the tidal problem. It's the same thing. It is possible to pull things off, but it wouldn't happen here, and that's fine. It's just a book. It's just for fun. So this was a little bit longer than I wanted to have it, but there you go. Calculate. The important thing is, how do you calculate the three-body problem, and then how do you calculate these stable orbits? That's the fun part. So code down below. Hope you had enjoyed this, but I hope you enjoyed this. If you've made it all the way to the end, that's great. And I will talk to you later.